today's session, we'll just see whether we can investigate further on symmetric points. Suppose Z is a symmetric point to itself with respect to a circle gamma. Okay. So we know by the definition of symmetric points that the cross ratio of Z, comma, Z2, Z3, Z4 is equal to the cross ratio Z, comma, Z2, comma, Z3, comma, Z4, the whole bar, because we are treating set star as said here itself. Okay, so this happens only if this cross ratio is real, right? And that happens only if all of the 4 points are lying on the circle. We all already know that set 2, set 3, set 4 are lying on the circle gamma. That means set will also lie in gamma. So we get a good note from there that set is symmetric to itself with respect to the circle gamma if and only if set is belonging to gamma. So now let's see if we can make some notes on symmetric points. Okay. So generally when we hear about the word symmetric point, we tend to think about symmetricity with respect to a mirror. Okay, that means suppose if this is a mirror here, sitting here, this line, we are keeping the point Z here, then you have the mirror image of the same point set star as the point sitting here, right? So whenever set and set star are symmetric with respect to the line, you can visualize it as a mirror. Okay. Our prejudice is that the line through Z and Z star will be perpendicular to the line gamma. That means here this will be 90-degree. Okay, perpendicular. And also that Z and Z star are at the same distance from gamma but on opposite sides of the mirror, right? So this is generally the concept that comes into our mind when we hear about the word symmetry. Okay, let's deal a case here. Suppose this gamma is a straight line. Okay, having set 2, set 3, set 4. All the 3 points are on gamma. Uh, and in that case, we have to choose one among them to be infinity. We had earlier uh, dealt with uh, a remark saying that if we are considering circles in C infinity, there is one possibility of the circle becoming a straight line whenever one among the points we are discussing is the point infinity. Okay, so that means the 3 points sitting here is actually a circle in C infinity and one among them is infinity. Okay, so that is a concept we are using here. So suppose if one among them, let set 4 be the point at infinity. Okay, and we are treating as set and set star to be symmetric points. That means they satisfy the equation of the cross ratio sitting here, right? Okay, and we know that set 4 is infinity. So when we defined cross ratios, we said that if set 4 is infinity, the cross ratio is having a different definition which is analogous to the main definition, and that is nothing but if we have the cross ratio z1 z2 z3 z4, if z4 is infinity, we'll have the cross ratio to be equal to z1 minus z3 divided by z2 minus z3. Okay, so we are using that here. uh, so we'll have, instead of set 1 we have set star here, so that is set star minus set 3 divided by set 2 minus set 3 is equal to, in the RHS we'll have, since set 4 is infinity, we have set minus set 3 divided by set 2 minus set 3 the whole bar. Okay, since set 4 is infinity, and we know that this can be written like this, like giving the conjugate on the numerator and denominator. Okay, since both of them are equal, their modulus will be also equal. And we know that modulus of z is equal to modulus of z, uh, modulus of z bar, right? So here we can, instead of this modulus of z2 minus z3 the whole bar, modulus of this whole bar, that is equal to modulus of z2 minus z3. So we can cancel out both of them in the denominators, and they are not equal to 0 because they are distinct, right? So you are getting a modulus of set star minus set 3 is equal to modulus of set minus set 3. Since the point set 3 can be taken as arbitrary, set and set star are equidistant from every point on gamma. Right. This set 3 is an arbitrary point, which we took, right? So the set and set star will be equidistant from every point on gamma because we can take, instead of set 3, we can take any point on gamma. Okay. Now, from the earlier steps, we had obtained set star minus set 3 divided by set 2 minus set 3 is equal to set minus set 3 divided by set 2 minus set 3, the whole bar. From that, we get this. And that means if these complex numbers are equal, the imaginary parts will be also equal. Okay, you get like this. And we know that uh, the imaginary part of here we can, instead of this, we know that this is equal to imaginary part of set minus set 3 divided by set 2 minus set 3, the whole bar, right? Both are the same. So that means this is equal to the negative of the imaginary part of set minus set 3 divided by set 2 minus set 3, because we know that the value, the imaginary part of a complex number and the imaginary part of a conjugate of that is nothing but the difference they are having, a minus 1 into minus 1, right? So that is the point to be noted here. Okay. So what you got here is imaginary part of this number is equal to negative imaginary part of this number, and you have to understand that the only difference here is this set star here and the set here and the negative here. Okay, so this will necessarily imply that the points set and set star lie in different half planes determined by gamma. Different half planes in the sense, like suppose if the circle is something like this. So this is one half plane, this is another half plane, right? So the set and set star will be lying in one of them. Like if set star is here, the set star is here, set will be here, like that. Okay. So please make sure that you are getting what the logic is behind in this equation. Okay. So now let gamma is equal to the center, a circle centered at A, the point A with radius R, okay, and R is 0 strictly less than R strictly less than infinity. And suppose you are taking 3 points, set 2, set 3, set 4 in this circle gamma, okay. Then suppose if set and set star are two symmetric points with respect to gamma, you get the equation like this, right? And on the RHS, you know that the cross ratios will be invariant when we apply Mobius transformations on them. So consider the Mobius transformation T1 of set is equal to set minus A. Okay. So instead of the cross ratio, the quadruple set 2, set 3, set 4, you can write the cross ratio of T of set, T1 of set, comma T1 of set 2, comma T1 of set 3, comma T1 of set 4, right? So instead of the function representation, you can write here as z minus a, z2 minus a, z3 minus a, z4 minus a, the whole bar. Also note that the cross ratio is like this, right? And the definition is like this. So that is nothing but applying conjugates on the numerator and denominator, and then again applying on the numerator and denominator. That is nothing but the cross ratio of z1 bar, comma z2 bar, comma z3 bar, comma z4 bar. That is an easy and analogy from that. Okay, so instead of this you can write this, the cross ratio of set minus a the whole bar, set 2 minus a the whole bar, set 3 minus a the whole bar, set 4 minus a the whole bar. Okay, and that, from that you are going to get something from here. Okay, you know that this set 2, set 3, set 4 are lying on the circle gamma. That means modulus of set 2 minus a is equal to modulus of set 3 minus a is equal to modulus of set 4 minus a, that is equal to r, right? So if you are applying the squares, that will be r square, and from that you get set 2 minus a into set 2 minus a the whole bar is equal to r square, set 3 minus a into set 3 minus a the whole bar is equal to r square. Set 4 minus a into set 4 minus a the whole bar is equal to r square. So you can substitute instead of set 2 minus a the whole bar, we can write r square divided by set 2 minus a. Set 3 minus a the whole bar is equal to r square divided by set 3 minus a, and set 4 minus a the whole bar is equal to r square divided by set 4 minus a. And instead of set minus a the whole bar, you can write set bar minus a bar. Okay. And then you are thinking about the next Mobius transformation, which is nothing but inversion and multiplying with r square. That is t2 of z is equal to r square divided by z. And that is a Mobius transformation. Of course, we had dealt with all those kind of functions earlier. So you are applying the Mobius transformation on the terms in the cross ratio, and they will be invariant. So we can write equal to, right? And then apply the t2 of z is equal to r square by z on each of the terms. So here that will be r square divided by z bar minus a bar. Here that will be r square divided by r square divided by z2 minus a, and likewise. Okay. And when you again then you again get the cross ratio of r square divided by z bar minus a bar comma z2 minus a comma z3 minus a comma z4 minus a. Now you are bringing forward the next Mobius transformation, which is just this z minus a uh, no t3 of z is equal to z plus a. Okay, just adding a constant. That is also a Mobius transformation. We had dealt with it before while dealing with Mobius transformation at first. Okay, so we are going to apply t3 on each of the terms in the cross ratio, and that will be invariant. So that is equal to the first term plus a, the second term z2 minus a plus a, z3 minus a plus a, z4 minus a plus a, and you will get this. Okay, so what we get finally is that the cross ratio of z star, z2, z3, z4 is equal to the cross ratio of r square divided by z bar minus a bar plus a, comma z2, comma z3, comma z4. And this happens only if z star is equal to this term sitting here by the definition of cross ratio. So from that you can rearrange to get r star minus a is equal to r square divided by z bar minus a bar, and cross multiply to get z star minus a into z bar minus a bar is equal to r square. And these two equations sitting here is a decent uh, observation we get about symmetric points. That means if z and z star are symmetric points, they satisfy the equations sitting here and here. Okay. So therefore, now we are considering z star minus a divided by z minus a. Suppose if z and z star are symmetric points, we get that z star minus a is equal to r square divided by z bar minus a bar, right? So substitute that here, and then you get r square is equal to this value here and this value here, and that is nothing but a complex number into its conjugate. So that is r square divided by modulus of z minus a the whole bar, right? Whole square. Okay, so this is definitely a positive quantity, strictly positive quantity. Okay, so this z is not a. Okay, so that z can be a, but this r is never zero, so this will be a strictly positive number. That is z minus z star minus a divided by z minus a is equal to some t, where t is a strictly positive number. So you can write z star minus a is equal to t into z minus a. So we are assuming that that is the strictly positive number. So that is nothing but z star is equal to t into z minus a plus a, where t is varying from 0 to infinity strictly. Okay. And this means that this z star is lying on the ray a plus t into z minus a. So that is a decent observation about symmetric points. And on the next set, we are going to just see what is symmetric principle, and then we'll define what the orientation of a circle is and see what is the orientation principle. And after that, we are going to move on to Riemann-Stieltjes integral. So that is all for today's lecture. Thank you for being throughout, listening and really watching out. So thank you again.